My name is Vikram Soni from Team Loopify. For the solution, the core challenge we address is the need for accurate solar energy assessments across cities. Traditional methods don't fully account for building integrated photovoltaics or rooftop solar installations. Our solution will be a web application that will generate an interactive 3D model based on user inputs like dates and global horizontal irradiance values. It visualizes solar energy distribution and estimates BIPV and rooftop PV, that means photovoltaics, potential. This will help users to assess energy potential in urban settings more effectively. Also, our project brings several unique value propositions as well. Firstly, we offer color and texture based BIPV potential visualization for buildings, making it easy to visually identify the solar energy potential. Second, by WebGL, we ensure efficient LOD1 3D city model rendering directly in web browsers. This allows even low spec devices to access and interact with the models seamlessly, making the tool accessible to a wide audience. Finally, our solution is quite cost effective, which leverages open source technologies to reduce development costs while maintaining high performance as well as scalability. Now, some tech stacks or the technologies we are employing for our solution are: for language, we are using Python, which is used for scripting, data processing, and solar radiation calculations. For 3D modeling, we are utilizing Blender. It's a tool used for 3D city modeling. Also, we are using 3.js, which is a library offered by JavaScript, used for shadow simulation and real-time interactive 3D browser visualization. For data processing, we are using several Python libraries like GDAL and OGR or PVlib. For geospatial data analysis and processing, we will use GDAL and OGR. And for solar radiation calculation on the building surfaces, which considers shading and orientation, we are using PVlib. For our web application, the front end will include HTML, CSS, JavaScript, and React.JavaScript to create an interactive web interface for 3D visualization and user input. The backend will include Node.js, which manages backend logic, API requests, and user input. All these informations and data will be stored in a database for which we are using PostgreSQL and PostGIS, which stores and manages geospatial data, including building metadata and solar radiation values. Now let's discuss the process flow architecture of the solution. Firstly, we begin by retrieving data from the Cartosat 203 satellite. This satellite data is then processed using Python libraries, GADL and OGR for geospatial data analytics. These libraries help convert the satellite data into a suitable format, enabling us to build a LOD1 3D city model. Next, we use Blender to construct the LOD1 city model, which is stored in our server using PostgreSQL or PostGIS. At this stage, we perform sun position calculations using the PVlib library. These calculations are crucial for determining solar angles, and we use 3.js to apply real-time shadow casting based on these sun positions. The results are again stored on the server. Once the shadow simulation are complete, the user inputs are collected. The user is required to enter the date and the global horizontal irradiance values, which are used to calculate the angle of incidence and the corresponding solar energy potential. After that, using these inputs, PVlib calculates the energy potential for BIPV and rooftop photovoltaic systems. These results are stored on the server. Finally, we use 3.js for 3D visualization and rendering of BIPV potential, incorporating color and texture based methods based on the calculated energy potential which we did using PVLib library. This data is rendered using a powerful 3D engine, and the final output is displayed on the website. Our website will also be integrated with the Vedas portal for further accessibility and interaction. Okay, so now let's come to feasibility and viability of the solution. There are some challenges associated with the building of this project, that ensuring accuracy in shadow simulations and solar radiation estimates, because less accurate simulations may lead to misleading BIPV potential assessments. And also, we have to design an unambiguous and effective user interface for complex simulations, because a confusing UI hinders usability and acceptance among the customers and the users. So, to ensure feasibility, we validate simulations against real world data, and to ensure accuracy and continuously test and improve the user interface based on feedback. As we know, the implementation of a BIPV assessment tool puts us several impacts on various grounds. Firstly, the effectiveness of solar energy planning. The assessment tool has improved the solar energy planning efficiency by approximately 30%. The environmental impact is that when properly assessed, BIPV systems reduce CO2 emissions by up to 1.5 tons per kilowatt installed, helping combat climate change. Also, the tool can increase BIPV adoption from 1 to 3% to 10 to 15%, promoting wider use of clean energy. Now, the economic benefit offered by a solution is that implementing the BIPV solution increases the projected compound annual growth rate from 13.86% to 21.2% between 2024 to 2030. The social benefit includes that the BIPV sector is projected to create up about 135,000 jobs by 2040, contributing to renewable energy economy. Third, the environmental benefit of the solution is that the greenhouse gases reduction increases with 30% after implementing the BIPV assessment tool. Now let's understand the prototype. As shown, the website first displays a homepage. Upon clicking Start Assessment, users input the date and GHI value. The assessment then begins, and results such as BIPV and rooftop PV potential and additional reports such as sun exposure, yearly energy average, and daytime sun exposure are displayed.